right, let's learn how to do a hypothesis test. And we're going to do one for proportions, like our confidence interval, and we're going to do one sample. So, aren't you glad you don't have to count what proportion of those dots are blue? Yay, no. Okay, so the hypotheses for proportions, there are three sets, and they are named according to which way we are looking for evidence to help us reject the null. So there are one-tailed to the left, one-tailed to the right, and two-tailed, or either way. And these are maybe the most familiar or the easiest to grasp initially. The null hypothesis says that the population proportion is equal to some number. Okay, so row 0 is a number. Row 0 will be a number. Okay, and the alternate says that the population proportion is not equal to that number. So it could be much less than that number, or it could be much greater than that number, but we're willing to look both ways for evidence. Then the left-tailed one-tailed says, okay, well, we're only willing to look for evidence that says that the proportion is less than a number. We're not interested if it's greater, we're just interested if it's less than this number. So that's what the alternate looks like. And then the null is the complement. So row is greater than or equal to that number. The right one-tailed test says, well, I'm only interested in looking at evidence of the proportion being greater than a number. Don't care if it's less. So the alternate is row is greater than the number. And then the null is that row is less than or equal to. Note that the equals part is always in the null. Okay, so the equals part of these two and equals by itself is always in the null. And then the alternate is something else. Here, the standard error of the proportion, because we have a hypothesized value, we can use that in the standard error. So whatever that number is, that's what we're going to use for the standard error here. And then the calculated z statistic, which is, this is our test statistic. That's the other thing that this is called. Okay, becomes the sample proportion minus the hypothesized proportion all over the standard error of proportion. And then we get a critical value, z of alpha for one-tailed or z of alpha over 2 for two-tailed. And you are accustomed to the two-tailed because we also use it in our confidence interval. And so that for 95% is plus or minus 1.96, and that's with alpha equal to 0.05 and alpha over 2 being 0.025 out in each tail. The one-tailed for a z for 95%, so z of 0.05 is either negative 1.645 or positive 1.645, depending on which direction you're looking. We will also learn to calculate a p-value, which is the tail probability associated with the z-calc from the table. So I'm going to just put in here the tail probability. And if you get it from the z-table or if you get it from p-norm, if it's a two-tailed test, so row not equal to row 0 is the alternate hypothesis, then you have to take your p-value and multiply it by 2. So p-value times 2. Okay? We're going to practice all this, don't worry. The number of tails tells you which way we're looking. And if you get confused about which way you're looking, look at the alternate hypothesis and follow the arrow. Now, Here's an example, and in this case there is no arrow in the alternate hypothesis because it's a not equals, which means we're looking both ways. So setting up this, and the idea is that we're hypothesizing that rho is 0.20, and we want to know if we get evidence that's extreme enough to convince us that it's not, that it's way out here. And so this is 95%. This is 0.025 or 2.5%. This is also 0.025 or 2.5%. And the z-score here is negative 1.96. That's a negative. So z, and the z here. And this is a critical z. Remember, that's the critical zone where we're critical of our null hypothesis. Okay, so the critical value in this case is z alpha over 2 is plus n minus 1.96. The computed test statistic, zcalc equals p bar minus p0 over the square root of p0, 1 minus p0 over n equals 0.175 minus 0.20 over square root of 0.20 times 0.80 over 400. So that equals negative 0.025 divided by 0.02 equals negative 1.25. And notice that that is right about there. Okay. So zcalc equals negative 1.25. It is not in the critical region, so it's not in, the other thing we call this is the rejection region. And it's not in the rejection region on either side. So our conclusion is that we fail to reject HO. Now there's a rule for this too, which is the absolute value of z calculated greater than the absolute value of z critical? And here the answer is no, because the absolute value of negative 1.25 is not greater than, in this case, the absolute value of negative 1.96 because it's off to the left. Okay. Now, we can also calculate the probability of finding something that far out with the p-value, and this is the probability of a z less than or equal to, in this case, negative 1.25. If this was a positive 1.25, we'd want the right-hand tail probability, so it would be the probability of z being greater than or equal to that number, but because we got a negative, it's negative that. So the probability is equal to 0.106, but because this is a two-tailed, we have to multiply that by 2 because it's two-tailed, meaning we were willing to look in either direction, and so that gives us 0.211 when we double that. Okay, and then the other question, so this is rule 1, is the zcalc greater than the zcrit. Rule 2 is the p-value less than alpha? And again, the answer is no, it's not, because 0.211 is definitely not less than 0.05. So the chance that we are wrong if we reject the null is a little bit over 20%. Alpha means we're only willing to tolerate 5%. So we're way over that. So we did all of that. And now let's see if we can bootstrap it, right? What do we get for a result that way? What we're going to come out with is a p-value. So with the bootstrap approach, we're going to simulate similarly sized samples from the null distribution. So we're using the proportion in the hypothesis, in the hypotheses. And then we compare the number of results that are more extreme than the result that we found. In other words, how likely is it to find a result as extreme as what we got based on what the null distribution should be? So you have the example code for this in your demo code. And what it gives you ultimately is a graph like this. And you can see here's our observed 0.175 or 17.5%. It's not that far out in the tail, right? Like here it is. Here's where things are getting really rare, and it's not that rare. The p-value for this is 0.2053. And that's very close to the 0.211 that we got before. So by hand, we got p-value of 0.211. So it was close. In both cases, both are greater than the 0.5% or the 5% or the 0.05. That we are willing to tolerate. Okay, so it doesn't seem likely that our guess is wrong. How about this question from before? Remember we said that the proportion of uninsured people was 8.5%, and then we got 10,000 people in a sample and found a rate that was lower. So can we see whether this has in fact decreased over time? Okay, so and first of all, let's talk about the hypotheses. So HO and HA. So what we want to know is whether it has decreased. So is the population proportion less than 0.085? Okay, and then everything comes up here the same except for the sign. So if this is less than, this is greater than or equal to. Okay, and we're only looking at evidence now. In this tail, and that is a very, very bad normal curve, but we're still only looking for evidence in that tail. So if you work this out by hand, you will get the zcalc equals 0.077 minus 0.085 all over, there we go, square root of 0.085, 1 minus 0.085 over 10,000, okay, which gets you this calculated z of negative 2.86. And you might remember that I said the one-tailed 95% to the left, the z-crit is negative 1.645. Okay, and that means that in this tail, you have all of the alpha, all 0.05 of it. Okay, and up here is the rest of the 95%. So is the absolute value of zcalc greater than that's question mark, absolute value of z crit, and in the correct tail. For one tail, you also want to make sure it's going in the correct direction. And remember, we are looking to the left, and we did get a negative number, so it is in the correct tail. And the answer to that is yes, because 2.8686 is indeed greater than 1.645. So what we're going to do here is reject HO, which means we have to accept HA. Okay? We can also either go to the table or we can use our p-norm and get the p-value. And so we could say p-norm negative 2.8686, and we will get 0.002. We do not multiply this by 2 because we have a one-tailed test here. Okay. So by rule 2 is 0.002 less than 0.05, yes. And so we would also, by that rule, reject the null. Now, if we do this with the bootstrap, and you definitely want to look at the code because the thing that changed is now we're looking at whether things are less than. Okay, so before we were looking at the absolute difference, now we're looking only for things that are negative. But the p-value using the bootstrap is 0.0014, which is even lower than the one we get doing it by hand. So that p-value of 0.0014 is definitely less than 0.05. So we think it's pretty unlikely. This is like a 0.14 of 1% chance of finding a proportion as low as 7.7% if the population was indeed still 8.5%. So it's pretty likely that this has indeed gone down. This is what it looks like graphed, and you can see here that our observed 0.077 is indeed much more out in the tail where things are unusual, and we're only looking in the left tail in this case. So there you go. Now, by the way, remember we said way back at the beginning, if n, the sample size, is sufficiently large, then we can use the z-curve and all that. So how large is that? So for means, you can use 30 as a benchmark, and we'll talk about that more later when we look at the t-distribution. For proportions, you want to test and see whether NP, so the sample size times the sample proportion, is greater than or equal to 10, and whether NQ, so Q, remember, is 1 minus P, is also greater than or equal to 10. And if there's not, then there could be a concern. And that would be one reason to use a bootstrap instead of the theoretical distribution. Now practice.